Alright, so this is
I could
section
only-
8.2, inverse trig functions. This continues off of what we started last chapter with graphing the trig functions and the reciprocal functions. If you didn't understand how the unit circle was broke up, if you didn't understand this unit circle and how it related to the triangles, your 45, 45, 90 and your 30, 60, 90, you're going to need to work on that. This chapter is very heavy on the unit circle and the triangles.
Oh, okay.
So make sure that you know those. So the first thing that we're going to do is we want to discuss what an inverse is. And it might be better to say what an inverse does, maybe. Or what it undoes. So we talked about inverses actually in chapter 3. What did an inverse do?
Yes.
It flipped us.
It flipped
added
what?
Asses.
Signs
The graph.
and X and Y, but X and Y.
Hang on, wait. What?
Over the origin.
What?
Which ones?
What are we talking about?
Wait, what?
Sine and tangent are the origins, right?
Mm-hmm.
It's odd. I don't know.
No, we're talking inverses. Inverses.
Oh, okay. Well, doesn't you can take that away.
Well,
You switch to X and
Okay,
Y.
so
Let's just think here for a minute.
So where it says how do we find an inverse? So that's where we switch our x values with y values. Okay, so that's how we find an inverse. But what exactly is an inverse? No one remembers what an inverse is?
It's got the -1 in front of it. That's the exponent, right?
So it's not an exponent, but it's the notation for it, yes, it'll have the
Yeah.
-1. So, okay, an inverse, essentially an inverse undoes, oops, did I spell right?
I can't even read, so don't even
It
feel bad.
undoes what a function did. And I'll show you what I mean in just a second.
Oh my god.
Okay, so if we have, say, an input, some number, we're inputting something. And we would put that into a function, say f of x, all right? We put something into a function, the function gives us something out, we get an output. What an inverse is going to do is it's going to take that output and it's going to take us back to the input. And like Nick said, the notation was f -1 of x. This wasn't an exponent, it's just the notation for an inverse.
Can't you like only say that after -1 if it is like a certain?
If it's a function,
Yeah.
that's the only time we can use this notation is when it's a function.
So is this like when we like flip the parabolas and stuff and you get like the horizontal?
It's going to kind of go along with that, yes.
Okay.
So function gives you the output to the input is your inverse function. So that's kind of what the next question is how can you tell if a function has an inverse function? So if you have a given function and you're looking to see if it has an inverse function. We talked about this in 3.6. There was a certain test that we did on a function to tell if it had an inverse
Horizontal line
function.
test?
Horizontal line test told us if a function would have an inverse function. And the horizontal line test said what? What did
If
we
it is, then
detect?
it cannot cross within one given point per line.
So if we drew a horizontal line on our graph and it hit the graph more than once, then that function was not going to have an inverse function. Remember that functions will have an inverse, but they may not be functions themselves.
Right.
It could be an inverse relation. So we wanna know when it's gonna have an inverse function. So then for that matter, how can we tell, or how do you tell when something, if something is a function? What'd you say?
Well, if you're
The vertical
seeing if it's a function, you just do a vertical line test.
So if we're just checking to see if it's a function, we do the vertical line test. And what did the vertical line test say?
Essentially the same thing. If you, any point should not intersect more than one point on the x.
So in this case, we draw a vertical line
It's like a parabola.
and we only want it to hit the graph one time. And that'll tell us that it's a function. So this is all information that we're gonna need when we're considering our inverse trig functions. So we're gonna talk about the inverse sine function first. And we're actually gonna go kind of way back to when we first started graphing sine. So we're gonna go back to using our t-chart. And I wanna graph negative 2 pi to 2 pi for sine. So that's plugging in, remember, all of those
Wonderful
values. So we had negative 3 pi over 2, negative pi over 2, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And remember, we can just kind of go off and do our pattern for sine rather than actually finding all of these. We know that we're on, above, on, below, on, above, on, below, and then back on. So we get those alternating zeros, ones, and negative ones. So if we were to graph this, we know that our function would just look like our normal sine curve.
True.
So we would get a sine curve that looks like that.
Are we gonna be dealing with a lot of like change increments and periods in this one, or is
No.
it just, okay, just making sure before I cry.
So now we want to talk about the inverse of the sine. So that's why I asked how we found the inverse, and you guys said that we switched the x and the y values. So we're going to take these x and y values that we have, and we're going to switch them. So we're going to have 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. And then we're going to put in our new y values. They're going to be our old x values. So negative 2 pi, negative 3 pi over 2, negative pi over 2, 0, pi over 2, pi, 3 pi over 2, and 2 pi. So now we're going to graph this one.
Not the snake.
So now our y values have the pi's. So we start at 0, this is pi over 2, and up, and then negative pi over 2 and down on our y-axis now. So if we started at our 0, 0, we could do our pattern that we're on, there, and then the same thing in the opposite direction, except now we're using the y-axis. So you're going to end up with a curve that looks like this. So now I ask the question, is this an inverse function?
Can you do the horizontal?
Why is it not an inverse function?
Because, first of all, the sine graph doesn't pass the horizontal line test, and then its inverse doesn't pass the vertical line test.
So
Thanks,
sine,
Jasmine.
so our sine graph doesn't pass the horizontal line test because if we draw horizontal lines,
She laid down the law. She's like, first of all.
you'll have multiple answers there. And this also doesn't pass the vertical line test because it hits multiple times. So this is not an inverse function. But the title of our section is Inverse Trigonometric Functions. So we have to find a way to make this an inverse function. So in chapter 3, we also talked about a way that we could make things that weren't functions into functions. And the way that we did that was we restricted the domain. So we're going to look at, rather than this entire curve, we're only going to look at a section of it. So we're going to get rid of this top part, and we're going to get rid of this bottom part. And we're only going to look at
Your
this
first
little middle section.
on off.
So if we're thinking about our sine curve,
Oh, Jesus.
that we know that this is the first quadrant because that's 0 to 2 pi. Then we have our second quadrant, third quadrant, fourth quadrant. So this section that we're looking at is actually this section right here in our table. That's going to give us this first quadrant and then this backwards quadrant. So that's going to be our first quadrant and actually our fourth quadrant, if we were thinking about that. So when we restrict our domain and we look at the unit circle, we know we have 0, this is pi over 2. If we're only interested in the first quadrant and the fourth quadrant, our values are going to go to pi over 2, and then down at the bottom this would normally be 3 pi over 2, but to keep it consistent, rather than doing 3 pi over 2, we're going to go back and do negative pi over 2. Because basically they're essentially the same thing. Negative pi over 2 is 3 pi over 2. Because we're just going back that negative 90 degrees. So when we look at these as graphs, we're only interested in quadrant 1 and quadrant 4. These two quadrants aren't going to matter.
Kind of like Kara.
Why?
Because we're restricting our area. So when we restrict our domain,
But isn't that the third quadrant?
what?
Like, isn't the graph in the 1, 3?
When you look at it here, it's 1 and 3, but that's not how we're thinking unit circle quadrants. So it goes 0 to 2 pi, and then it would go to pi, 3 pi over 2, and then back to 2 pi. So when we look at our values, this goes from 0 to pi over 2. This goes 0 to negative pi over 2. So that's where we get this 0 to pi over 2 is quadrant 1. 0 to negative pi over 2 is quadrant 4. So that's why we're only interested in 1 and 4 for sine. So on the next page,
I know.
at the top, it tells us that the inverse function is called the inverse sine or arc sine function and is denoted by g of x equals sine to the negative 1 x, or like I said, the inverse sine, or g of x equals arc sine of x. So either notation can be used. They mean the same thing. And remember that negative 1 is not an exponent, it's just the notation used for inverse. So we need to define the domain. So remember that the domain is the x values that you put in. So on our graph that we restricted on the other side, what were the x values that we put in? What were the possible x values?
-1, 0, and 1.
So negative 1, 0, or 1. So we went from negative 1 to 1. So all the values in between negative 1 and 1 is our domain. And then our range. What were the possible y values that we could get out on our restricted?
Negative
Oh, no.
pi over 2 to pi over 2.
So that went from negative pi over 2 to pi over 2. So when we're thinking about arc sine or the inverse of sine, these are the new domain and range that we have to be thinking about. So when we talk about the inverse, we're gonna use it to find different things and to answer different questions. So when you use the inverse sign, it answers the question, what angle has sine equal to opposite over hypotenuse? So that's kind of a confusing statement.
No.
So what the diagram shows is kind of like what we were talking about when we put something into a function and then we did the inverse function. So for sine, we're given an angle when we use the sine function. We're given like sine of pi over 3 and then we have to find this opposite over hypotenuse. So we're putting an angle into the function and we're getting out the ratio. Well, with the inverse sign, we're going to have the ratio and we want to get back the angle. So in this case, we'll have like inverse sine of root 2 over 2 and we need to find the angle.
So we can assume that some of them are rational?
They can be, yes.
Let's not.
So when we're solving for arc sine or inverse sine, you're looking for an angle. So we have some examples down here that we're going to do. We have 7 examples. The first 4 are simply using arc sine and inverse sine to find the angle. The bottom 3 are composite functions. So remember that was like your g of f of x. So you found your inner function part and then you put it into the outer function. So when we get to those, we'll see how those work. So for number 1, we want to find the arc sine of negative root 3 over 2. So just a reminder again, we're only looking at quadrants 1 and quadrants 4.
So if it's negative,
So if it's negative, where are we going to be? We're going to be in 4, and if it's positive, we're going to be in 2, or in 1,
One.
sorry. So positives are in 1, negatives are in 4. So we need to find where root 3 over 2 is, negative root 3 over 2 is. So we just said that our negatives are going to be in quadrant 4. And we know that sine is opposite over hypotenuse. So we're going to have our opposite, this is the angle that we're looking at. Our opposite is negative root 3, and our hypotenuse is 2. So now we need to ask ourselves, what angle is this that your opposite is root 3 and your hypotenuse is 2? So Nick said 60. So if it's a 60-degree angle, what's that in radians?
Pi over 3.
So that's a pi over 3
Or
angle.
like 5 pi
But-
over.
Now wait, you 5 pi over what, yes. However, we're looking specifically for this angle. We went backwards.
So negative.
So this is a negative pi over 3. Remember, our angles need to be between pi over 2 and negative pi over 2.
So now now instead of going like 5 pi over, we're
Mhm.
just talking in terms of just flipping the sign.
Yeah, you're literally going off of the x-axis from 0. You're going off of the x-axis in the positive direction and the negative direction.
Okay.
So this is just a negative pi over 3.
no, it's fine, it's okay.
Does everybody understand that? Chelsea, are you okay with that? Okay. Well, I'm just making sure because you had questions about the quadrant, so I just wanted to make sure. Sit down. So now we're looking for inverse sine of 1 over 2 or 1/2. So this time we're going to be positive. And again, we have opposite over hypotenuse, so 1 and 2. And we're looking for this angle this time. 45, 90.
No, you're 30.
So this one, remember, is,
Halfway there.
You're
this
so
is your
smart.
30, 60, 90 triangle.
I'm halfway there.
So this is a 30-degree angle. And what's your 30-degree angle?
Over
Pi
6.
6.
Pi over 6. And this is a positive pi over 6.
It's not too bad.
Number 3,
Wait, I have a question.
yes.
How come, like, arc sine and sine, how come we're doing opposite over hypotenuse for arc sine too? Is that just what it
Because
is?
it's still, you're still looking at the sine, so you still know that it's opposite over hypotenuse. But now, instead of figuring out that ratio, you're figuring out the angle that gave you that ratio.
Okay.
So this one's exclusively for sine. What we're doing right now is
Yes.
exclusively for
So if it says arc sine and sine, you just go about it the same way?
Yes.
Oh, wait! It's sine negative 1, I didn't even see that. Never mind.
Those are just the two different
Ways to
notations.
say
Oh,
that.
yeah, I did.
They mean exactly the same thing, they're just the different
It's
notations.
not amateur hour, Jasmine.
So now, this time we have arc sine of -1. So this is where we remember that sine was y over r when we defined it as when we were using the unit circle.
So if
So our y value is
Okay.
-1. So we're gonna be down here at 0, -1. So if we're at 0, -1, what angle is that? Between 0, that was pi over 2, that was -pi over 2. So if we're at 0, -1, we're at -pi over 2.
Genius.
Then we have arc sine of 0. So again, that's still our y over r. So our y this time is 0. So that means we're here at 0, 1. Or at 0, 0, sorry.
1-0.
So in this
If I could
scenario,
write it, it'd be great.
so in this
1,
scenario,
0.
after we restricted it, it's never 2 pi, it's always just 0.
Hmm?
So in this scenario, after we've restricted it, it's never gonna be that 2 pi,
Mhm.
even though it's there.
Mhm. So here we're at arc sine of 0. So we haven't gone anywhere. So what's our angle? 0. So when you're on the axes, you're gonna have one of your axes values. So this was 0, pi over 2, -pi over 2. Now, the last three are composite ones.
Ew.
So what you're going to do is you're gonna do what's on the inside first. What you get from that, you're gonna plug into the outside value. So we're gonna do inverse sine of -1/2 first. So that's gonna be down here, and we have opposite
So negative pi.
over hypotenuse. We need to find that angle. So what did you say? So it's -pi over 6. So this equals -pi over 6. And then what we're gonna do is we're gonna take that sine and plug in -pi over 6. So that -pi over 6 was right here. And we need to find the sine of -pi over 6. So that's opposite over hypotenuse. So you get back that 1/2.
Is it always gonna come out to the same thing?
So you don't have to do anything out of
No,
That's like-
because there's like cosine.
Well, yeah.
So for this one,
Um,
so what did we notice? We're finding the inverse sine, and then we're
You're just
doing
going
the
back and
function.
forth.
So it's just going back and forth.
But that's only if you have the inverse of the same operation.
Yes,
Okay.
yes, that's only when you're taking the sine of the inverse sine. So for number 6, this time we're taking the cosine of the arc sine.
Ew.
So we're gonna find the arc sine first,
It's my hair.
and again, we have that -2 pi over 2. Now this one is one that you would want to look at as being rationalized.
Which is upsetting.
So when you rewrite this, it would actually be 1 over root 2. Remember when we rationalize that? So now for your arc sine, you're going to have opposite over hypotenuse. So you have -1 root 2. And again, we're looking for that angle.
Negative pi over 4.
So we have a -pi over 4. So our arc sine gives us a -pi over 4. So then what we're going to do is we're going to take that -pi over 4 and put it into the cosine. So now we need to find cosine of -pi over 4. So we need to know what this third side is.
1.
So that's just a 1 because this is our 45, 45, 90 triangle. So cosine of -pi over 4 is adjacent over hypotenuse. So 1 over root 2 or root 2 over 2.
So this one is just that it
So
They
this
made
one
it
just got rid
positive.
of the negative in this case.
Is that always the scenario for arc sine to
I
cosine?
don't know. I don't think so.
Yeah, let's make rules.
What?
Just,
So, and then our last one.
no, they're over there.
Can anyone guess what our last one might be?
Oh my god, it's gonna be pi over 3. No,
Negative pi over 3.
It's gonna be pi over 3.
Kara, I hate you.
And we can tell that because we're gonna take, this time we're taking the sine of pi over 3 and then we're putting that into the inverse. So it's just the opposite of what we did back here. So this time we're gonna get back the angle. So in this case, we're gonna do, we know our pi over 3 angle is here. So this is pi over 3. And then we need to label our triangle. So across from pi over 3, we have our root 3, that's a 1, and our hypotenuse is the 2. So we find that sine of pi over 3 is root 3 over 2. So then we're going to take the inverse sine of root 3 over 2, and that gives us back that pi over 3. Because you're looking for which angle gives you an opposite of root 3 and a hypotenuse of 2.
Make you like radius person as
So
well.
those two rules that we actually just went over, for when you take the inverse sine of the sine function for a certain value, you get back your u. But it's important to look at the restrictions. Your u value, so whatever angle you're putting in, has to be between that
Sorry.
negative pi over 2 and that pi over 2. It needs to be within that interval. Now, for the inverse, if you're taking the sine of the inverse sine of a ratio, and you get that ratio back, you can do that as long as your b value is between -1 and 1. So it's important to pay attention to these guidelines. Those will tell you if you can actually do this. And that's what this example is actually going to show us, that it wants us to explain why sine inverse of sine pi over 6 equals pi over 6 is true, but inverse sine of sine 5 pi over 6 equals pi over 6 is not true. So that's going to be looking, for the first one, we're going to look at sine of pi over 6. So we know pi over 6 is in the first quadrant. And then we need to label our triangle. So we have 1, 2, and root 3. So we're going to take the inverse sine after we figure out the sine of pi over 6 is 1/2. We're going to take the inverse sine of 1/2. And that equals that pi over 6 back. Because you're looking for what angle is your opposite 1, your hypotenuse 2. So that one is true. Now, for the inverse sine of sine of 5 pi over 6. 5 pi over 6 is in the third quadrant. That gives you your 5 pi over 6. So when we draw in our triangle, we know that we have a pi over 6 angle left here. So that's like our reference angle, remember? So again, labeling our graph, we have 1, or our triangle, we have 1 root 3, and then 2. So when we find sine of 5 pi over 6, we have opposite over hypotenuse, which is again 1/2. So then we're looking for the inverse sine of 1/2. So when we go and draw that out, we know that we have opposite over hypotenuse, and this time we're looking at this angle. So that gives us back our pi over 6 angle. So we don't get that 5 pi over 6. And that's because that's not in our range of values that we could have for angles. So does everybody understand how these two properties work? Alright, so now we're going to start talking about cosine. And we're going to do the same thing that we did for sine. We're going to start by graphing our original cosine curve from 0 to 2 pi. So we're gonna have 0, pi over 2, pi, 3 pi over 2, and 2 pi. And again, using our pattern, we were above, on, below, on, above. So then when we actually graph it, you just get your normal cosine curve. So now we want to graph the inverse the same way we did the sine inverse. So that's switching our x and y values. So we're going to have 0, 2 pi, 3 pi over 2, and 2 pi. So again, basically now we're going up the y-axis rather than using the x-axis. So we'll start at 1, 0. And work our way up like that. So we get that cosine curve. Now again, is this an inverse function?
No.
No, this isn't an inverse function again because it fails the vertical line test. So again, we're going to restrict our domain like we did with the sine function. So for cosine, we're going to get rid of this top section and just look at this bottom part. And just like we did with sine, remember that this was the first quadrant, the second quadrant, third, fourth. So now this time, we're looking at values from 0 to pi over 2, and then this goes up to pi, because remember we have our y-axis labeled pi over 2, pi, and so on in those increments. So this time we're looking at this section, this top section. So this time, again, we have to restrict the domain. This time we're only looking at the first quadrant and the second quadrant. We're not interested in anything below here. So we're looking at values from 0 to pi for cosine. So again, on the top of the next page, it tells us that this inverse function is called the inverse cosine or arc sine function, and is denoted as cosine -1x or arc cosine of x. Remember again that these mean the same thing, they're just different notations. So now this time, the domain for cosine. So the domain again are the x values that we're putting in. So they're the same as the sine function, we're putting -1 to 1 values in. And then we're getting out for our range 0 to pi values. So that's our new domain and range for the inverse cosine. And then just like we did with sine, we're gonna find the arc cosine and also the composites of the cosine. So again, this time, remember that we're looking at 1 and 2. And that cosine is x over r. So we're going to be positive in the first quadrant and negative in the second quadrant. So for the first one, we're looking for -√3 over 2. So we're going to be over here. And remember that we're measuring from 0. So we're actually looking for that angle. You measure from 0 to where your angle is going to be. And this is your -√3. And then your hypotenuse is 2. Remember that this is adjacent over hypotenuse. So again, we're going to use this as our reference angle to help us figure out what this bigger angle is. So we know that this is our 30, 60, 90 again. And what angle is this?
5 over 3.
So,
30, whatever.
so we're gonna end up with 5 pi over 6, because we know that this angle is our pi over 6 angle. So we're looking at the pi over 6 angle in the second quadrant, which is 5 pi over 6. That's why the unit circle is so important. If you don't know that, make sure you do. Number 2, we're looking for the inverse cosine of 1/2. So this time, we have adjacent over hypotenuse, and we're looking for this angle from our 0. So we know that this is root 3 again. So, again, we're in our 30, 60, 90 triangle, and what angle is this? This is a pi over 3 angle, or a 60-degree angle. And then number 3, we have arc sine of -1. So this again goes back to cosine being x over r. So if our x value is -1, we're over here at -1, 0. And this is also our pi area. So from there to there, our angle is pi. Then we also have composites for the cosine, just like we did with the sine. So for this, again, we're going to do the inside, and then put that into the outside.
Just be -1/2.
So we're going to be over here, we're going to go -1, and our hypotenuse is 2. Again, we're looking for that bigger angle. So this is, again, our 30, 60, 90. This is a 60-degree angle, reference angle, so that gives us, this bigger angle should be,
5 or 5, no, I messed up, 2 pi over 3.
so it should be 2 pi over 3. So we're going to put 2 pi over 3 into cosine. And we want to find the cosine of 2 pi over 3, which is adjacent over hypotenuse, which gets us back our -1/2. So again, this goes back to, you're taking the inverse function, putting it back into the function, and you get that number back. For number 5, we're taking the sine of the inverse cosine. So for this one, we have the inverse cosine of root 3 over 2. So we have adjacent over hypotenuse. We're looking for this angle. That tells us that this is a what kind of angle? It's a pi over 6 angle, or a 30-degree angle. So we're going to put sine, and we're going to take pi over 6. So sine of a pi over 6 angle. So remember, that's opposite over hypotenuse, which gives us 1/2. So the sine of the inverse cosine of root 3 over 2 is 1/2. And then finally, number 6, we're taking the inverse cosine of the cosine of pi over 3.
It's a mouthful.
So this goes back to, again, the properties,
Which is fine.
that it's just going to be pi over 3. But to show that,
Mm.
we know that our pi over 3 angle is here. We know that that would be root 3, 2, and 1. So the cosine of pi over 3 is adjacent over hypotenuse. So we're going to take the inverse cosine of 1/2. Because we found that this equals 1/2. When we do that, we get our pi over 3 back, because we want to know what angle has an adjacent side of 1 and a hypotenuse of 2,
Right.
and that's our pi over 3. And again, that's these properties down here. If you take the inverse cosine of the cosine function, as long as your angle is between 0 and pi, you should get that angle back. And if you're taking the cosine of the inverse cosine of a ratio, as long as that ratio is between -1 and 1, you'll get that ratio back. Right, you can go ahead and stop.
And it has some